Aloha and welcome to Live from NOIRLab at Hawaii. My name is Jamika. I am an outreach assistant here at the International Gemini Observatory, a program of NSF's NOIRLab. Joining me today are two amazing guests I'm really excited about. First, I will introduce to you Steve Howell. So Dr. Steve Howell is currently a senior research scientist at the NASA Ames Research Center in Mountain View, California. Let me highlight his video so that you can see him while we're speaking.
Folks, how are you?
Thank you, Steve. So Steve, yes, is currently a senior research scientist at the NASA Ames Research Center in Mountain View, California. He was formerly the head of the Space Science and Astrobiology Division and the project scientist for NASA's premier exoplanet finding missions, Kepler and K2. And I have to say here, Steve, it's one of only two missions that I have followed completely from beginning to end. The other one was Cassini at Saturn. So Steve received his PhD in astrophysics from the University of Amsterdam and has worked in many aspects of astronomy, including pioneering the use of charged coupled devices, or CCDs, in astronomy, building new instruments for ground and space-based telescopes, and public outreach and education. Steve is also involved in formal and informal scientific education for kids to adults, and this includes his participation in Super Chefs, which is a nonprofit organization teaching food science and healthy eating to young adults. Steve has edited and written 2 science fiction books related to exoplanets and space travel, along with about 800 scientific publications, numerous articles, and other books that he has also co-authored. He lives in San Francisco Bay Area with his partner Sally and enjoys scientific challenges, the great outdoors, vegetarian gourmet cooking, and playing blues music. And yes, he still considers Pluto to be a planet. Steve, you may get some comments in the YouTube audience about that. All right, so welcome, Steve. Thank you so much for being with us today.
Thanks, Jamika. Happy to be here.
Our second guest today is Rachel Matson. And let me bring up Rachel. So Rachel is an astronomer. Dr. Rachel Matson is an astronomer at the U.S. Naval Observatory in Washington, D.C., where she conducts observations for the Double Star program and manages the orbit catalog within the Washington Double Star, WDS, database. Her research uses Speckle Interferometry to detect and characterize double stars, as well as determine whether stars with transiting exoplanets found by NASA's Kepler and K2 and TESS missions are single or actually double stars. In this case, we refer to those as binaries. Rachel earned her bachelor's degree in physics from the University of Denver and a PhD in astronomy from Georgia State University. She now lives in Maryland with her husband and adopted greyhound, Lee. Welcome, Rachel.
Thanks for having me.
And today I am serving as your moderator. So those of you in the YouTube audience, I'll be joining you shortly. Your comments and questions are welcome throughout the presentation. So your host today is going to be none other than Peter Michaud. And Peter is going to introduce himself. But as a reminder, very quickly, Peter is here on screen as host. I will be sending questions to him and to Steve and Rachel throughout the presentation. So over to you, Peter, and everyone else. I'm about to join you in the YouTube Live audience.
Hey, thank you very much, Jamika, and I'm thrilled to be here. And Rachel and Steve, I'm glad you can join us today. I don't want to take too much time, but I do want to share a little background information on NOIRLab and specifically on the Gemini Observatory, and show you one of our featured science results that has recently come out. I'm going to switch my screen here, I believe, if all goes well. And let's see here. I think I know how to do this. Okay, let's share that. Play that. How's that? Is that making sense? Okay.
Yes.
So I just wanted to give you a little background information on specifically the Gemini Observatory, because we're coming to you from, or at least I'm coming to you, and Jamaica is also here in Hawaii, and Hilo, Hawaii. It's a rainy day in Hilo today. Hilo is the wettest city in the US, and so we're proving that today. Up on Mauna Kea, though, another part of the Big Island where we're located is where the Gemini telescope is located. And you can see in the background here, we've got some videos that show what the telescope looks like from the inside. To give you a sense of scale, the telescope's about 7 stories high, and we're looking at it under the illumination of a full moon in this video. And so if you didn't know that the sky was blue at night, it is when the moon is shining, for the same reason it's blue during the daytime. But oh, and here we are on the outside. Oh, yep. Now we're looking at Mauna Kea. About 14,000 feet high. That's where Gemini North and the other observatories of the Mauna Kea observatories are located. And one of the things you can see from this animation is how the clouds tend to stay down, capping out at about 9,000 feet. Because of that, the summit area of Mauna Kea stays nice and clear and dry. And as the sun goes down now, we can see the moon will come up again, and you'll see the mountain at night. And you can see how those clouds stay well behaved down below the summit area to keep things clear, dry, and stable so that we can do astronomy up on Mauna Kea. So that's where we're coming to you from today on the Big Island of Hawaii in Hilo. We have 2 telescopes. Gemini has 2 telescopes. That's why it's called Gemini, the twins. We have one in Hawaii in the middle of the Pacific and one in Chile. And so collectively, those both telescopes can see both hemispheres. Zoom a little bit in on the Hawaii Islands. The Big Island is the big one down there on the bottom. Zoom in a little bit more, and you can see the snow-capped tops of Mauna Kea and Mauna Loa. Mauna Kea is the one near the top of this image. And you can also see down there a little red glow, and that was the satellite picture was taken when the volcano was more active than it is now. The volcano on the Big Island, Kilauea, has recently quieted down a bit as compared to what it was a few years ago. Mauna Kea, by the way, is a long dormant volcano. It's not extinct. It's been about 4,500 years since it's done anything. So we feel pretty confident putting our observatories up there. You know, over time, geologically, it's still potentially an active volcano. Our headquarters are in Hilo, and you can see this is where our control room is located. Even during COVID right now, we are operating at night at Gemini North, and so our operators will be in there at night working, making observations. And again, we have 2 telescopes, Gemini, one in the southern hemisphere, one in the northern hemisphere, Gemini North, Gemini South, and collectively they can see the whole sky. And I think when Steve and Rachel talk in a little bit, that's one of the advantages that they take advantage of too, having instruments on both telescopes, very innovative instruments, I might add, that they've been responsible for putting on the Gemini telescopes on both hemispheres. Okay, I'm going to skip over that and go to a view of what the telescope looks like as we're about to go on the sky at night inside the dome. You can see the observing slit there, and then the vent gates on the side that keep everything very stable from a thermal point of view and keep everything at the same temperature, which is desirable for a telescope in order to see things as clearly as possible. And finally, I just want to highlight a recent result. Many of you may have gone out and seen Comet Neowise in the nighttime sky over the past few months. We've been observing it at Gemini. And one of the things that we've been looking at are the jets coming out of a comet. A comet can be described as kind of a dirty snowball. It's made up of ices and gas and dust. And as it gets closer to the sun, it warms up and the gases sublimate. They go from a solid to a vapor and are often emitted in the form of jets. And what we're looking at here is those jets, or at least one of those jets, that is sort of spiraling around as the comet rotates. It rotates, this particular comet rotates about every 7.5 hours. And with these observations, we're able to get its rotation period very, very precisely. And again, you can see in this sequence of images how that jet sort of spirals around. It's kind of like if you took a garden hose and spun it around your head, the water would come out and sort of make a spiral shape as it spins around. So if you did get a chance to go out and see that comet, it's getting pretty faint now, but we were able to observe it with the Gemini telescopes and make some significant observations and understand its rotation a little bit better. And with that, I'm going to stop sharing and turn it over to, let's see here, how are we doing there? Turn it over to Steve, who will put his slides up and talk about the Speckle Imaging at both of the Gemini telescopes. Steve and Rachel, thank you very much. We all set now?
Yeah, we're all set. Thanks, Peter. Thanks, Jamika. So Rachel and I are part of a team that works on this technique called Speckle Interferometry at the Gemini North and South telescopes. And we'll tell you a little bit about that today and how exciting these instruments are and what kind of science we work on using them, as well as some members of the community. And at the end, I'm just going to talk about a few things that we're starting to play with, some new ideas that are somewhat unrelated to our main science topic, but somewhat fun for us to do, and scientifically very exciting for the community at Gemini. So this is a picture of Gemini South. Peter showed us some lovely videos of Gemini North. This is Gemini South. You can see, other than the mountaintop, it looks pretty much like Gemini North. They're essentially twin telescopes. So for us, that was a big advantage, because when we made our instruments, we could make the same one just twice. So let me start with a little bit of description here of angular resolution, because we're going to be talking about pretty small regions on the sky. And so I thought I would just give you a little introduction to what angular measurement is, if you don't know this, and try to give you a feel for how tiny pieces of the sky we actually can observe with our instrument. It seems like you might think, oh, that's bad to only observe a tiny piece of sky, but I'll try to tell you why it's really good to only observe a tiny piece of sky. So in the top left here, there's a circle that's drawn, and you might remember from geometry that a circle, if you go all the way around the circle, that is, and you measure it in degrees, that is 360 degrees. That's all the way around. So if I take one little pie slice of that, and that's what's shown on the left there as 1 degree, then I can divide that. If I go to smaller angular measurements, that 1 degree is divided into 60 pieces, and each of those pieces is called an arc minute. And then I can divide each of those arc minutes again by 60, and each of those is called an arc second. So it's kind of like a clock at some point where you go from minutes to seconds, and 60 minutes is an hour. Here, 60 arc minutes is 1 degree. And then 60 arc seconds is at 1 minute. So to try to give you a feel for what that means, you've probably all looked up at the full moon at night. So when you look at the full moon, the size across the full moon is about 30 arc minutes. So it's half a degree across. And the little picture there below the moon shows you ways you can measure angular parts in the sky. So if you have those 3 fingers held up, that gives you 5 degrees. If you have your 2 fingers like the Hawaiian sign up, it gives you 15 degrees. And so it's various ways to measure rough sizes in the sky. But all of those, remember, are in degrees. And we're going to talk a lot today about arc seconds. So we're going to talk about the smallest little measurements. And to give you an idea of what that might mean, if you can imagine this in your head, if you took a dime coin, a US dime coin, that's the little thing on the bottom there with Roosevelt on the picture, and you gave it to your friend and you told your friend to walk 2.5 miles away from you, and then you could even imagine seeing that person or that dime, the size that that dime would make to your eye would be 1 arc second. So you might not know exactly what it is, but I bet you can get the concept of it being a very, very, very small, little tiny angular measurement on the sky. And so we're going to be talking about these small angular measurements for good reason, as you'll see. I can go to the next slide. Perhaps I can't go to the next slide. Oh, there we go. All right. So here is a video that tries to show you the science we actually do. These are actual images on the left. These are called Speckle Images, and you can see they look like a bunch of speckles. That's why they're called Speckle Images. In the middle is just a sum of all the images on the left, one laid on top of the other, laid on top of the other, laid on top of the other, and summed together to give you this image that looks kind of like a broad dot here. And that's the kind of image that normal telescopes see when they look at the night sky. When they look at stars, they look like dots. So if you've looked at the night sky with your eyes, you see stars that look like points of light. If you get out binoculars and you look at the stars, they look like points of light. If you get a big telescope and you look at the stars, they mostly all still look like points of light. And that's because they're so far away in most cases that you can't resolve them into anything but a point of light. But on the right-hand image here, you can see that there are 2 dots that appear. And this is what our instrument and our mathematical techniques that we use do. We take images like those on the left, we apply something called Fourier analysis to them. It's a mathematical technique. And we can make an image that's equivalent to the image on the right. And in fact, this particular object isn't one single star. This particular object is 2 stars that are very, very close together in the sky that cannot be separated by other means, by typical other means. But they can be separated by this technique of interferometry like we use at the Gemini Observatory. And I show on the bottom of this image that white bar, which is that measurement we talked about in the previous slide of 1 arc second. So this is a tiny piece of the sky. But if we want to know that if that star in the middle is 1 star or 2 stars or sometimes 3 stars, we need to use some technique to get a very high resolution image and turn it into, in this case, into these 2 stars. These 2 stars actually orbit each other. They're a binary star, and we'll learn a little bit more about those later on. And this is for those of you that might care about the geekiness of Fourier analysis and mathematical techniques. So this is a mathematical construction, which is called a power spectrum. So it's one of those techniques in the Fourier analysis, but this shows you what looks to be a very boring type purpose, but it's actually a very good purpose. And that is, if I have a star that's a single star, so not a binary star, not 2 stars, but a single star, our imaging of it looks like the image on the right, and the data we collect looks like the image on the left. So the cleverness here is that a dot looks like a dot. And you think, wow, that's pretty impressive. A dot looks like a dot. Okay, but here's the really cool part. In this particular case, now I have on the right a star that really isn't a single star, but really is a very close binary star, a pair of 2 stars that, again, hardly anybody else could ever detect without our instrument and telescopes like Gemini. And what we measure is that shown on the left. We measure this pattern of lines called a fringe pattern. And so if our mathematical technique shows us that fringe pattern on the left, we know that we've seen 2 stars and not 1 star. And we can convert that fringe pattern into this image on the right of these 2 stars. So that's what we do. That's the technique we use here. This is the original use of this technique called Speckle Interferometry. This was done at the famous Mount Palomar Hale 200-inch telescope in the 1970s. So 1970s was long ago for some of you, and long ago for the rest of us too, but long ago. And in this technique, I don't want to show you really anything here about this, and the words are all things you can read or whatever, but I just want you to look at the top row of pictures here. And these are the speckle patterns. These are what a star looks like if you observe the star very fast. So for example, when we take images at the Gemini telescope, our integration time, that is how long we look at the star, each of these speckle frames is only 60 milliseconds long. So we can take 1,000 frames in 1 minute, and each of those frames kind of looks like this speckle pattern. And you can notice here that the speckle pattern is different for different kinds of stars. And that's really all this diagram is trying to show you. And in particular, if you notice the middle speckle pattern, the thing under the star Alpha Auriga, which is also known to some of you as Capella, it's a very bright star in the sky, you can see it with your naked eye. You can see that the speckle pattern there is actually doubled. There's a dot for each of the stars in this close binary, where on the other two stars, you see that each speckle is just a speckle by itself. So right away, once these patterns start becoming familiar in your brain, you can notice that this middle star is going to be two stars, and it's going to create this fringe pattern as we see on the bottom here. So if you came and sat with us at the telescope for one night, you would see lots and lots of these speckle images as we're observing, and you eventually would be able to notice that for yourself. So we don't do this by eye, though. We actually do it all with computers and mathematical functions to get it very precise. But you could, in principle, do it with just your eye if you had a bright enough star. So we're going to talk today a little bit about a number of these topics, but not all of them, because we could be here for a week doing this. And mostly we're going to talk about exoplanets and what we do for exoplanets. But I wanted to just provide a list here of the types of science that our instrument is supporting at Gemini North and Gemini South. And some of these might mean something to you, like solar system objects. I'll show you later an example of us looking at the planet Saturn. Other of these, like X-ray stars or Gaia support, might not mean anything to you. And so you could ask us a question about that maybe, or you could look it up online. So I don't want to spend much time on this. I just want to get on to exoplanets here.
Steve.
Yes.
Is it okay if I jump in here with a few comments from our YouTube audience?
Absolutely. I didn't see your picture show up, so sorry if I missed you.
No worries. No worries at all. So we have first quite a few colleagues, NOIRLab colleagues in the YouTube live audience. So I want to say thank you and welcome to all of our NOIRLab colleagues. And to all of our visitors, period, who are here today for our presentation with Steve Howell and Rachel Matson. So Rachel and Steve and Peter, we have a few comments here and already a question for Rachel and Steve that I've been asked to ask at the end, so I'll hold that one. Peter, we have a comment for you from Dr. Travis Rector. Travis says, hi, Peter, and he's hailing from Anchorage, Alaska, so we're absolutely happy to have Alaska with us. Also, we have a few comments from Josepher. Steve, as you were talking about giving us that intro into Speckle Imaging, I was asking a few questions in the audience about the topic, and Josepher says that it was Speckle-tastic, which I thought was fabulous. We also have Ariel Vallejos, who's joined us from Argentina. Peter, Ariel really enjoyed the NEOWISE comments that you were making and showing about the rotation, but unfortunately Ariel said they could not see NEOWISE down in Argentina because it was too close to the sun. So those are our current comments. Those of you in our audience, please keep those comments coming and questions as well too, and I will jump into the presentation at an opportune time to share them.
If I can just add real quickly that Travis Rector, who sent his regards, he works with us in creating a lot of the very pretty pictures that we get from NOIRLab. And so thanks, Travis.
Thank you, Travis. We definitely appreciate that. And in fact, Ariel asked about, said that when it said they couldn't see Comet Neowise down there, I shared one of our NOIRLab images in the chat. So we definitely appreciate all that imaging support, Travis. All right, back to you, Steve and Rachel.
Okay, thanks, Jamika. Hi, also Travis. Travis is a longtime friend of mine as well and science collaborator. So how are you doing? Good. All right, so I want to just talk a little bit about the Kepler Space Telescope and the fact that it was finding planets that orbit other stars. That was the point and the mission of the Space Telescope. And I show you this because this is going to lead into why our work with Speckle Interferometry, and in particular, why looking at such tiny little pieces of the sky is so important. So I have in this slide an artist concept on the top left of the Kepler Space Telescope looking at some star that in this case is awfully close to it, but it's just a concept, and looking at these planets that might be orbiting that other star. And on the bottom, I wanted to show you what the stars look like if you look through binoculars or a telescope at the sky, and you've probably seen this or you've seen images of stars like this, and they look, as we mentioned, like a bunch of dots of light. And to the right of that, this sort of square blocky thing is what Kepler sees if it looks at that same field of view. So that one bright star fills up these 4 very large imaging elements called pixels in the Kepler field of view. And all those other stars, all those faint background stars, are kind of lost in that light of that star. So while Kepler was great at measuring the brightness changes of stars, it wasn't very good at getting a nice picture of a starry sky. Its pictures were all sort of these blocky, square-like star patterns where a lot of light from a lot of stars were blended together, making it sometimes very difficult to know which star or any of those stars actually caused some kind of brightness change. So what Kepler was looking for, and I have this animation, and with help of people, I think I figured out how I can do this. So let me see if this works. I think it's supposed to loop through. So the idea in this animation is to show you what a transit is, a thing called an eclipse by a planet, which is called a transit. So as the planet orbits around the star, when it passes directly in front of the star, it blocks some of the starlight. And if you're measuring these data from some telescope like Kepler, you measure those blue points on the right, and you can draw a white line through those blue points, which is sort of a nice fit to them or a nice model. But as the planet's in front, you see that the brightness of the star gets a little fainter. And as the planet moves away, the star becomes bright again. And that dip allows you to know that something passed in front of that star. And we'll also notice that you can't tell here, but I'll show you in the next slide, that the size of that dip tells you the size of the planet, assuming you know the size of the star. The other interesting thing to notice here, which we won't talk about, but it's just kind of fun in this video, which is pretty realistic, is you notice how the bright part of the planet changes its brightness and its phase. It actually has phases like the moon, where we have a new moon, a quarter moon, a full moon, which is hidden by the star, and then a phase on the other side again. And you can actually observe this in our solar system. If you watch the planet Venus as it orbits the sun, you can see these phases on the surface of the planet Venus. It looks like a little miniature moon phase of half moon and full moon and quarter moon, things like that. So we won't talk about phase anymore, but planets actually do this, and astronomers have been able to measure that phase change on the surface of a planet. Okay, let me see if I can get out of here now and go to the next slide.
Steve?
Yeah.
While you're making that transition, could we ask Rachel a question?
Sure, absolutely.
Okay, Rachel, if you
can answer for Rachel. Sure, you can answer.
Yes, thank you. I know I was interrupting you while you're transitioning. Want to make sure that was okay. Okay, Rachel. Steve is giving us a lot of interesting background on Kepler, K2, and TESS. Could you give us just a little bit of info on when the Kepler mission started and roughly the duration?
think I'll have to get the launch date from Steve, actually, because I don't remember the exact year. It was
2009.
2009. Thank you. I was going to say 7 was when I got started to get learning about it, but I didn't think it was so. 2009 is when it was actually launched. And the idea for Kepler was to stare at one patch in the sky and look at those same stars for kind of as long as possible, but ideally at least about 4 years. And so Kepler actually succeeded in getting to about 3.5, almost 4 years of just staring at this one patch of sky. And the great thing about this is if you're looking for planets, especially a planet like Earth that takes a full year to orbit its star, if you only look at a patch of the sky for a year or less, you can't find planets that are in such kind of wide or long orbits. And so being able to stare at one patch in the sky for 4 years, you could find planets. Ideally, usually you want to see more than one of these transits, but you can at least get to a year, maybe 2. After about 3.5, almost 4 years though, basically some of the stabilizers are what helped Kepler point in one specific sky. Not enough of them kept working to keep it pointed so precisely. And so it started looking at different regions of the sky for shorter periods of time. But that was, so then it kept going for another couple of years afterwards. So the kind of the prime mission or the main mission was almost 4 years. And then K2 beyond that had another couple of years. And really they just finally shut down the mission and a lot of the support for it, the last maybe 1.5 years, 2 years, something like that. So it was quite a long mission and we're still working on the data from it.
Fantastic. Thank you, Rachel. Steve, anything you want to add to that point?
No, that was great. I think we can show them some real data from Kepler here.
Fantastic. Thank you.
All right. Thanks, Rachel. Nice setup for this. So here I want to show you on the right-hand side some real measurements from Kepler, and on the left-hand side some artist concepts of what we would be measuring. And remember, I'm just going to go back to one slide here. So remember, we're looking now at graphs that are like this graph on the right here, these blue dots. So as the planet orbited, remember it made that dip. So here they're white dots and that, but it's the same thing. So in the top example on the left, if we could see our planet Jupiter pass in front of our sun. So you can't see this from the Earth because Jupiter orbits outside of the Earth, farther away from the sun than the Earth. But if you went out to my favorite planet Pluto and you watched Jupiter transit the sun, this is what it would look like if you looked in a telescope. You'd see this big black circle going across in front of the sun. And on the right is the measurement you would make of the light of that star as a planet of the size Jupiter passed across the front of that star. So on the right here are real data from Kepler, and you can see in this top one that the star gets fainter in the middle in this kind of big U-shaped dip, and the graph or the axis on the bottom is just time in hours. So this is about 30 hours long. So it takes about 30 hours here in this particular case for this planet to pass completely in front of the face of its sun. And you can see this dip is quite easy to see. In science, we would say this has a great signal to noise. That is, it's quite an obvious result. Anybody here would see this dip and say, wow, I see the light has become fainter here. And this particular planet was about 9.7 times the radius of the Earth. So that's roughly the size of Jupiter. And its orbital period was 330 days. So it's a Jupiter-sized planet that orbits this star about once every Earth year. Now on the bottom, on the left, is again an artist concept of what the Earth would look like going across or transiting in front of our sun. And I don't know if you can see the little dot, but there's a little tiny dot there. That's all the bigger the Earth would appear to be. And where Jupiter blocks about 1% of the light of the sun when it's in front of it, the Earth would only block about 0.01% of the light. So that means that the little dip you see, and that's shown here on the bottom right, is very tiny. The little dip here is just hardly any amount of change in light at all. And so what scientists do is, if you look on the bottom right there, you see the white dots are the actual measurements. And you can convince yourself, I think, pretty well that something in the middle has caused the light to sort of go down a little bit. There's a little dip there. But because all these measurements are independent, you can do something called averaging. You can take all those white points and you can average them together over time, in this case, the 8 hours that this plot shows, and you would get those orange points. Those are the average values of all those white points. And then you can even help a little further and draw a line through all those orange points, which is a model that you should see. And you can see now, I think you're pretty well convinced here that there's actually a dip in the light here, that this star had something very small pass in front of it. And this is in fact a confirmed planet now called Kepler 20e, very exciting name. And it's a little smaller than the Earth, and it orbits its star every 19.6 days. So these are the kinds of measurements that Kepler makes by looking at stars and watching and waiting for the light from those stars to have a small little change, a small little dip in it, indicating that there's a planet or possibly a planet that passes in front of that star. This is a plot or an image here just to kind of show you that while we would love all of the cases to be a single star and a single planet, things can get pretty messy and pretty complicated. And that could be that you could have, in this case, the top left image here is exactly what we want all the time. We want a single star and a single planet. And we know that the dip is caused by that planet, and we're all very excited and we believe it's a planet and we move on with our life. However, there are many other things that can happen here. For example, in image B, if you have a very small star, very low mass red star, or even something called a brown dwarf, they're about the same size as the planet Jupiter. So if they pass in front of their star, the dip looks about the same as if it's a planet about the size of Jupiter. So that can be confusing to us. In part C, you could have a nice bright big star, but in fact that star could be a very close binary star. That's the other little yellow star there. And that other little yellow star could have another star that orbits it. And you could have a binary star that's near in the sky to another star. And it's really the dip of the binary eclipse that is happening, not really a dip of a planet. You can also have a case like D, where you have two stars orbiting each other, but they don't directly pass in front of each other. They just sort of cut off a little bit of the light of each other, called a grazing eclipse. And you could go on and on making up these cases of what else could cause the dip. And so this is where people like Rachel and I come in, because we're going to try to help understand what really causes that dip. Is it all of these other confounding cases, or is it really a planet? Rachel, you want to talk about these graphs here? I'll give you the easy ones or the hard ones, whatever.
Sure. Steve mentioned previously that part of the, well, I guess you saw when we looked at the difference between a Jupiter-sized planet and an Earth-sized planet when they pass in front of their star, the dip of the star is deeper. And so, but another thing that can also affect that is if you have kind of extra light in the system. We'll talk about that in a minute. But what's being shown here is this observed transit depth. That's how deep that curve is. And then you can see that's corresponding to the image that Steve just talked about, where it's just a planet crossing in front of a star. And then on the bottom is just an equation, but what it's saying is that basically the depth of the transit gives you an idea about the size of the planet. So the size of whatever object is passing in front of the star. So in this case, if you have one single large star and you have a planet passing in front of it, we can get the relative size, so how big the planet is compared to the star. And so that's just the equation showing that down on the bottom there. If we move to the next slide though, so this is similarly, this is where I started to mention if you have extra light into the system. So you can see now the image on the right now shows a star and a planet, but there's now a small red star off to the left. And so that star is contributing extra light to the area, the pixels, the area that Kepler is measuring. And so there's more light. And when there's more light, that causes that change, that little dip in light to look shallower. And so you can see that the observed transit depth at the top of this plot is shallower or smaller. And because you have a smaller transit, you are then thinking that the planet is smaller than it actually is, because it's that relative depth of the transit that gives you the size of the planet. And so this is concerning because if you are measuring, you're saying, oh, look, we found a planet that's roughly Earth size, but there's extra light being added by a nearby star, you're actually measuring what looks like an Earth-sized planet is actually larger. And so what we're going to talk about in a minute is actually trying to find if there is other light, sometimes called third light, in the system that is changing the transit depth that you are measuring.
Thanks, Rachel.
Yeah. Jamika, did you have something?
I did, yes, thank you. And thank you for those last comments, Rachel, on clarifying that. Thank you, yes. Okay, so we have lots going on here in the YouTube live chat. I've been talking about transits and asking the audience if they had heard of the Kepler mission and knew what a transit was. And I was explaining how the transit method works. And then we had one of our NOIRLab colleagues, Robert Sparks here in the chat, who had it detailed and said, if the planet moves fast, it's called a rapid transit. Have you all found any rapidly transiting exoplanets, Rachel and Steve?
Well, the transits that have been detected by Kepler, K2, and TESS, I would say they span quite a range of timescales. So I don't know exactly where you go from rapid to slow, but for example, a planet in a 1-year orbit takes about 13 hours for the entire transit to happen. So it would appear to be in front of its star, hiding its star and making that dip for about 13 hours. Where a planet that's been found in this class of planets called ultra short period planets, and these are planets that orbit a star like the sun, and amazingly, they have orbital periods of less than 1 day. I mean, it's just amazing how quickly they orbit around their star, and therefore how close they are to the star. So those transits can last only a minute or so. So there's quite the range in time from very short transits to very long transits. And in fact, the ultra short period transits tend to be only found because while they orbit across so quickly, and you might only have one data point that's in that dip, but you see those transits every 2 times a day, maybe for years. And so you can add up many of those orbits and eventually see that there is something transiting there.
Thank you, Steve. Awesome. We are excited about this presentation. We're getting lots of comments, questions, people excited about finding some images and knowing about how many exoplanets are out there. So I have some questions for you both that I'm holding to the end. So this is really engaging and you got a lot of people talking. So we'll let you continue.
Sure, sounds great, thanks. All right, so here I just want to get back to showing you some images again, to try to give you this idea of scale and what it is we're looking at and why we again need to look at such a small part of the sky at each time. So on the left here are 2 bright stars. This is a picture taken from a telescope on the ground, kind of a telescope you might have in your backyard. It shows 2 bright stars and a few other faint stars there. In the middle is that same field of view, but this is what the Kepler spacecraft image looked like of that same image. So again, you can see those 2 bright stars, and you can see that in the top right corner, there's in the left image, there's 3 stars, and in the right image in Kepler, you can only see kind of 1, and the rest of the stars are kind of faint, and they're all this sort of square pattern. And if I now show you what the latest NASA Exoplanet Space Telescope program would see. Let me see if I can click on this. There you go. So this is what this same image would look like to the NASA TESS mission. So now the pixels are so big on the sky that those 2 stars are completely blended into one sort of rectangular mess. And so all of these images represent a Kepler discovered exoplanet that exists on the star in the middle. Can you see my cursor, Jamika?
Yes, I can see your cursor.
No, can you see the cursor that I'm moving?
Yes, I can see your cursor that you're moving.
Okay, good. So everybody can. So this star right here in the middle is the star that Kepler found an exoplanet around. TESS has also looked at this same field of view, and so it saw the transit too, but from TESS and even from Kepler, you aren't necessarily sure what is actually transiting, what star it is, because it's such a weird, compilation of these big square stars. And from the ground, you wouldn't be able to see this transit at all because the dip is so small that you can't detect such tiny changes with a telescope on the ground due to the Earth's atmosphere. So here's 3 cases where we believe we have a planet, we believe we have a dip, but we want to be sure. So we observed this object with our Speckle camera at Gemini. That's the 2 images on the bottom left. And it was also observed with the Keck telescope, also on Mauna Kea, using a technique called infrared adaptive optics. And you can see on the bottom that we now see 2 stars and 2 stars and 2 stars. And you might wonder, why are the 2 stars on the bottom not the same orientation as the 2 stars on the top? Well, that's because the scale of the boxes on the bottom are the size of this white scale I've shown you up here. If you can see on the top left, there is now a little white box that's appeared. I can take it off, put it back on. You see that little white square? So that's the size of the field of view that we are now representing on the bottom. And it turns out that that middle star, the star that has a planet orbiting it, is actually a binary star. It consists of these 2 stars on the bottom, this very close pair of orbiting stars. And now the trick is, which of those stars does the planet orbit? And that's not always a very easy question to answer. And in fact, in this case, I don't think we know the answer yet. Which of those stars does the planet orbit? So here is just a sort of graphic cartoon of the kinds of simple cases that we might discover. On the left is the case we all know and love. This is the one we hope everything was. It's 1 star, 1 planet. In the middle is the case of a binary star system where you have 2 stars, a planet orbits 1 of those stars. And on the right is a case that's even harder to figure out, but could happen. And that is, you now have 2 stars, but those 2 stars aren't the same brightness. And the planet could orbit the fainter star, and therefore the planet is really much bigger than you would think it is compared to the case in the middle where there's 2 stars, but the 2 stars there are similar. So to find the true size of the planet, you need to understand the details of whether the star itself is single or binary. Okay, Rachel, did you want to add anything to these about binary stars here?
I don't think so. I think you just made a great point, though, is that kind of like we were saying, if you have an extra star nearby, it can make the planet look bigger. You can think the planet is smaller than it actually is. And similarly, if the star that the planet is orbiting is actually a smaller, dimmer star, that makes the planet bigger as well. And so it's not, so we have to understand the whether or not there's extra light in the system to understand the size of the planet, and also make sure we understand which star is actually being orbited.
Okay, thanks. So
Before we move on, I apologize, Steve, may I jump in here real quick?
Sure.
Just a heads up to everyone that this is our 10-minute warning. 10 minutes until we wrap up. And so I would like to say that we definitely have a couple of questions waiting for you, Steve and Rachel, which I'll come back in a few minutes to share. But I also just wanted to make sure that you were aware of our time so that you could make sure you had enough time to finish your presentation. And a quick question for Rachel. Rachel, could you give us just a brief insight into how many exoplanets have actually been discovered and confirmed by Kepler in the K2 mission? Just a rough number.
So I believe the current number is something like 4,000 have been transiting planets have been confirmed with Kepler. A lot, there's kind of, it's hard to figure out this confirm, but basically in order to confirm that it's a planet, you can either look at it in different methods, for instance, spectroscopy, get its radial velocities and its mass, or you can do kind of the way, like we've been talking about here, is look and make sure there are no other stars that could be influencing the transit, and any other, basically kind of rule out any other possible causes. If we can rule out other nearby stars, nearby binaries, a small star, things like that, then we can say we're pretty confident it's a planet. And so that's kind of what they use. It's confirmed now. And so there are, I think it's roughly 4,000, but there are people still going back and mining the Kepler. And again, as Steve mentioned, the TESS mission, they're still working. They're about 2 years in. They're finding more planets. There are other surveys going on. So there's still lots to be found and lots of candidate planets that haven't been confirmed yet. But I believe the number is around 4,000 currently.
4,000. Wow. Thank you so much, Rachel. Okay, so Steve, I will come back in about 5 minutes with our last questions and to begin our wrap up before we head it back over to Peter.
All right, so thanks, Jamika. I'm going to zoom along then. So I just want to quickly get through some slides to show you folks the instruments we actually built. They're called Alopecia and Zorro. And for those of you that maybe don't know what those words mean, these are words both mean fox. Zorro is fox in Spanish and Alopecia is fox in Hawaiian. And we use these names to sort of honor the local peoples and languages, but also because we thought fox was a cool idea for our small, fast, and clever instrument. This is Nick Scott, another person in our group, when we were building these instruments at the NASA Ames Research Center. Just to show you what an instrument looks like, I'm going to go through these kind of quickly so we can get to your questions. Here's a computer-aided design of the instrument, which is how we build these things these days in our local shop. This is the telescope and the instrument actually being mounted on the telescope. I tried to use the purple arrows to point to the instrument on the left. It's the kind of black thing on the right side there mounted to that big white face. And on the right image here, the right arrow points to the instrument and the left arrow points to all the power supplies for all the parts of the instruments. So the power supply box is actually bigger than the instrument itself, which is pretty unusual for a modern telescope instrument. And I wanted to highlight just a few cases here to show you the power of this. You may have heard of this very famous planet called Trappist 1. It was a very low mass, very red star, but really close to the Earth astronomically. It's only, I think, about 10 light years away. And this system was found to have 7 planets orbiting it. Our solar system has 8 or 9, as you might know. These 7 planets, of course, all orbit in less than 20 days. So the star is much smaller than our sun and much cooler than our sun. So you can orbit much closer in and still not be very hot or be, very close to the star because it's smaller. This diagram is real pictures on the bottom, but an artist concept on the top of what those planets might look like. And 2 or 3 of those planets that are roughly Earth size, which means that they're probably rocky surfaces, orbit in the so-called habitable zone. So these planets could have life. But as we just heard from Rachel, if this star was not a single star, if this star was a double star, then all these planets would really be bigger than we think, and they could be bigger by a factor of 2 or 3. And therefore, instead of being small rocky type planets like the Earth, they would be more like planets like Neptune. So we wanted to confirm whether this star was single or not. And we made this measurement from Gemini South. And much like that first image I showed you, that a point source turns out to be a point source and it seemed boring. Well, here, that's why it's so exciting. This is an image of the star that those planets orbit called Trappist 1. And on the right, I just show you that same image with some scale of what sort of size we're looking at in and near this star. So we're looking at about the size of the orbit of Mercury out to about the size of the orbit of the planet Uranus. And we showed by this work that there's absolutely nothing else in this system brighter than sort of a planet Jupiter. So that is no other stars are anywhere in this system. So those planets are really the size we think they are, which is very exciting because some of them are small and rocky and in the habitable zone. And I just want to show you one last case here to exemplify when there are problems. So here's an object called KOI 2626. It's a candidate planet that Kepler found. This is the Kepler image of it. And now you know that these blobby things are what Kepler sees for stars. And if this was a single star, this planet would have a radius of about the size of the Earth. But when you look at this closely, it turns out with our instrument, this star is not one star, but it's actually 3 stars. And these 3 stars are all very close together in the sky. And now we don't know which of the stars the planet orbits, but we now know that the planet is not really the size of the Earth. It's actually 2 to 3 times the size of the Earth, because these other stars were providing other light that was diluting the signal. So this is one of the cases where it didn't turn out to be so simple, and now we don't know which of these stars the planet does orbit. I'm going to skip some things here just to show you one fun fake news point. Here's a picture of a 5-pointed star that we took during an instrument commissioning run, just to let you know stars really do have 5 points. Maybe you'll ask me a question about this one, how we know stars have 5 points. And let's see, I just want to get on to showing you Saturn and Jupiter, because I promised you I would. So here's a picture of Jupiter and Saturn on the left with just taking a picture with a telescope. And on the right is one of our first attempts at trying to make that image much sharper by using these techniques, these mathematical techniques that we've developed. So I think with that, Rachel, if you have some final words, otherwise let's go to Jamika and take some questions before we run out of time.
All right, I think Steve pretty well covered what we did, but basically the idea behind, the initial idea at least behind these Speckle instruments at the Gemini telescopes is really to be able to do what's called follow-up imaging. And so when we have these exoplanet candidates and we're not really sure if they orbit one star, or if there's multiple stars adding light, or potentially a second star that the planet's orbiting, basically the goal of these instruments is to go in and be able to look at those, get those really high detailed close-in images in order to figure out if there's other light from multiple stars or nearby stars in the system. However, these are great instruments. The Speckle technique has long been used to study double stars, to monitor their orbits, to study them in different parts of the galaxy. And because these instruments are basically really fast imagers, because as Steve mentioned, we take something like 60 millisecond images. There are a lot of other techniques that people are trying to use these for. And so Steve kind of highlighted a list of those early on in the presentation, but there are some really neat things being done with these instruments beyond just this. But this was kind of the initial kind of goal of the program and what Steve and I are really involved in.
Thank you so much for that, Rachel. Okay, last few questions here at the end. All right, so here in the YouTube audience, first I want to say thank you to everyone for joining us, all of our guests and all of our NOIRLab colleagues. We all appreciate your support and for being here. Okay, so a few questions. First is from Ariel Vallejos. Ariel asks, can this process, Speckle Imaging, can it be used to improve increase the angular resolution in VLBI programs like the one used in the M87 Horizon event for future campaigns?
Rachel?
That's a good question. I'm not very familiar with what she's specifically talking about, but VLBI uses long baseline interferometry. So it's kind of a similar technique, but actually separates telescopes apart rather than just basically doing a mathematical transformation like we do. So it's a way to basically get the angular resolution of a single dish telescope down to what's called its diffraction limit, its kind of very limit, where long baseline interferometry kind of uses different technique to use individual telescopes separated over very large distances to increase the angular resolution.
Anything you want to add to that, Steve?
Well, there is a very famous, Rachel went to a school where she got her PhD that's known for doing interferometry. And they have an interferometer at Mount Wilson, which is outside of Los Angeles, called the Chara Array. And this is an interferometer of optical telescopes. The black hole telescope that your question was about is an interferometer of radio telescopes. But yeah, it's this idea you have telescopes and you separate them by in the radio case, the size of the Earth, I mean, miles across, and in the Chara optical interferometry case by hundreds of meters. And it works as the equivalent of a telescope that had one mirror that's that big. And you can put the images back together and basically get a very high resolution picture because no one can build a telescope that big. But it's a way you can do it. So that's a kind of interferometry, and ours is a kind of interferometry. So they're similar but different, but they attain the same goal.
All right, thank you. And this last question from Ariel before we head it over to Peter, because we are already 1 minute over. Last question is more about exoplanets. Is it true that more than 90% are multiple systems of exoplanets?
Does the question mean that planets exist in systems that have more than one planet?
Yes, it says, yes, I believe so. How many multiple planet systems have we found with Kepler? And is that common to find multiple planetary systems?
Yeah, that's a really good question. I don't know if it's 90%. I guess I haven't really looked at that in great detail, but there are certainly many, many multiple planet systems. I think the record is 9 planets that we know orbiting one star, and not our sun. This is another star that has 9 planets. There's a number with 8, a number with 7. But the real trick is if I look at a star and I see a planet orbiting with, say, a 1-year orbit, there might be a planet with a 10-year orbit. But if I only look at that star for 2 years, I may never see that 10-year planet transit. And so what we did find from Kepler was that if a star was found to have 1 planet, it was more than likely that if we kept looking at it, we would see more planets.
All right, thank you, Steve. Rachel, anything you want to add to that?
No, I don't think so. Just it's a matter of, like Steve said, I don't think we haven't found a lot of the planets. So while we think we found a lot of single planets around stars, it's still to be discovered if there are more around all of them, or if half of them are single versus, or 90% of them have companions. So it's still a work in progress.
Fantastic, thank you. Okay, so I'd like to thank both of our science guests. That is Dr. Rachel Matson and as well as Dr. Steve Howell. So those of you in our YouTube audience, thank you so much for your questions and comments. Again, we are always so pleased to have our NOIRLab colleagues here with us for support and feedback. Thank you all so much. And after we post the video, we will have links to the Kepler and K2 missions, the TESS mission, as well as links to Alopecia and Zorro that Rachel and Steve mentioned, are instruments here that they've used at Gemini North and South. And we will also have a link to the paper that uses this imaging process that Steve and Rachel and one of our Gemini colleagues, Andy Stevens, authored. So that will also be in the video description. Over to you, Peter.
Thanks, Jamika.
Well, I'll just, since we're running over, I'll just say thank you again to Rachel and Steve. I appreciate that. A lot of great information and great science that you're doing. And we're looking forward to a lot more and having you back next time when you make even more discoveries. And join us each week for Live from NOIRLab, coming from, Jamika, I think next week's is coming from Tucson, correct? And then Chile. So we rotate between the 3 sites of NOIRLab between Tucson, Chile, and Hawaii. So join us, and thanks everybody for participating.
Yes, thank you everyone so much. And we'll leave our last comments to our special guests, Steve Howell and Rachel Matson.
Great, well, thanks a lot, Peter and Jamika. Thanks everybody for watching, and remember, keep looking up.
I can't top that.
Sounds good. Thank you all so much, everyone, for joining us, and we'll see you next week. Aloha.
Aloha.
Aloha.